There you go. So hopefully today is going to be more fun. We try to understand why the networks that we've seen so far, about which we have computed, calculated quantities, and established some facts based on empirical analysis, why they look the way they do, and what it takes for them to look the way they do. So this is it's going to be the bulk of today's class, today's lecture, network models. We will introduce some recipes basically to build models build networks from scratch, which ideally mimic the structure of real networks. And towards the end, however, I would start talking about dynamic processes running on network, which is usually one of probably the most fun part of network science. People would like to see epidemic dynamics running on contact networks, or I mean, although of course it's a bad thing by itself, but it's a nice exercise and good skill to acquire. And also information spreading or diffusion, opinion dynamics, rumor spreading. This is going to be then the rest of the menu for Tuesday, but I want to make sure that you're aware, of course, of these things starting today, because it may give you idea about the projects that you will eventually choose to do. And take the chance to remind you that the slides are already available. They were already available before the course started. So the slides of the last class, in case you're curious and you want to get more ideas about potential projects, project pitches, tomorrow and Friday, they're already available. So just go to the Dropbox folder. If you have any problems to access it, let us know. We can send you the files otherwise or solve your access problem. Okay, let me then start with the slideshow. Like I said, network model. These are the four models we discuss. They are classic models, especially the first three. The last one is my way to say that there are ways to explain the three key features that we have learned / discovered, depends how familiar you were with these things before you joined this course. So this model indeed generates networks with those three features. And we're going to go through that multiple times, and we're going to test whether the networks that we build with these models obey those properties or not, which properties are satisfied, which properties are there, which ones are missing, and what we can do to reproduce the missing features and so on. So this is going to be the key or the exercise we're going to do today before we move to information diffusion as a first example of network dynamics. Okay, so let me recap what we learned in the past 2 days. We defined a bunch of things, we measure a few things, but overall, I would like to attract your attention towards three key facts, which seems to be sufficiently general. And this is part of the fascination of network science. These networks that you build from very different contexts, where the nodes can be anything from people to routers, to websites, to proteins, to species, that these networks share, with of course few exceptions, but overwhelmingly share a set of common features. The first one is the small world property, first one in order of discovery, because the Milgram experiment, which was of course only intended for the network of acquaintances between people, so a social network, but as I showed you, and this table that I already showed you testifies that the small world property, the fact that you can go from any node of a network to any other node of the network with a few steps. This is the average number of steps going from one node to any other node. And you see this number is very small, however, much, much smaller than the size of the network, which is represented by the entries in this first column of numbers. So first fact then, short path. We can easily go from one node to any other node. Of course, we need to know how to do it, because we must have some sort of perception, and apparently humans are very good at finding this path, which is highly non-trivial, and say something about the structure of those networks, but this is a problem we're not going to be tackling in the context of this course. But there are short paths, small world. Second thing, there are a lot of triangles. So surprisingly, there's a surprisingly high density of triangles, given that most networks of interest, and certainly those that you see in this list and many others, are sparse, as I mentioned multiple times. So there are many more missing links than there are links. There are many, many, many more pairs of nodes which are not connected to each other, then the person knows which are actually connected to each other. And to form a triangle, you need three links. You need A connected to B, connected to C, connected to A. So it takes somehow, you need some links to do that. So if you're not so many links around, the question is how come that you have then so many triangles, high clustering coefficient? More often than not, except for very specific networks like bipartite networks, in which by design, the clustering coefficient, which has a measure that gives a feeling about how many triangles are in the system, is systematically equal to 0. But like I said, in defined bipartite networks here, the important thing is to see that these numbers are fairly close, are not so far from 1, and definitely much farther away, very far away from 0, 10 to the minus 3, 10 to the minus 4, which is what you can expect to find in random networks with the same number of nodes and links of these systems. And I'm going to tell you in a while what I mean by random networks. So second property, a lot of triangles. Short path, so small world property, a lot of triangle. I see somebody wrote something in the chat. This is the same transitivity. This is exactly transitivity. The clustering coefficient quantifies the transitivity property. But physicists, computer scientists don't know/don't like the word transitivity, although it was the original concept introduced to explain this property in the field of social network analysis. So third and last property, of course, there are many others, but these are the three pillars that we try to stick to build our networks. Heterogeneity. Real networks are heterogeneous. There are hubs, there are nodes which have much higher degree, so many more neighbors than most of the others. And again, this table that you already seen before, specifically this column here, with this number called the heterogeneity parameter that we introduced yesterday, gives us a sense of how heterogeneous with respect to the degree distribution, with respect to degree, these networks are. As I mentioned, when I introduced this measure, values of this ratio close to 1 indicate that the nodes are have mostly the same number of neighbors, approximately the same number of neighbors, whereas values much sufficiently larger than 1, whatever that means, right? Because you need to be quantitative, much larger than 1 or larger than 1. I mean, not just strictly 1.1 and so on, like twice 1, 2, 3, 5, 10, 20. Like most of the numbers you see here indicate that there is some heterogeneity. The more the higher the heterogeneity, the higher the value of this ratio. So for instance, in this case, the Wikipedia math network, which is an information network of Wikipedia pages dealing with math. This is a directed network. Has a heterogeneity parameter, which is in this case is computed for the in-degree distribution, almost equal to 40. So it's extremely heterogeneous, which means there are some pages which has really lots of pages pointing to them. So yeah. Okay, so three things: small world, a lot of triangles, and heterogeneity, the presence of hubs. When we introduce a model, we would like ideally to explain this property, to reduce this property, make these properties emerge from some simpler assumption. And that's what a model is. It's a set of instructions, a set of assumptions, or it's a recipe basically to build a network, in this case, a network model. And ideally, we would like, of course, to build networks which resemble the networks that we've seen so far with respect to the existence of these three properties. Here you see again, Paul Erdős. We mentioned him yesterday when we talked about social distance, died in 1996. And when he did, he interrupted an incredibly intense period of activity that saw him publish hundreds and hundreds of papers with more than 500 co-authors. That's the reason why we mentioned him yesterday. And there could be other reasons to mention him in very different contexts. The reason I mention him today again is that he is also one of the founders, the two co-founders of random graph theory. This is because many years ago, between the 50s and the 60s, they introduced a model and developed and studied its properties and developed and derived some conclusions from, really rigorously proving theorems. These are real mathematicians, so they prove theorems, so they really derive exact truths about what seems to be, and probably you're going to have the same feeling after I introduce it, if you're not familiar with that, seems to be the simplest way to generate networks with noise, in the presence of really the highest possible uncertainty. And the idea that is at the base of this is that we place links at random between pairs of nodes. There are two versions of this model, which turn out to be equivalent, which were proposed at about the same time. We will be dealing, and usually the literature spends much more time on the Gilbert random network model, which is improperly called the Erdős-Rényi model. I may use this notation as well. The good news is that they are equivalent. The bad news is that if you improperly call models, you are depriving people from credit they would deserve to get. So the model we discuss here, the version of the random network, our random graph model that we'll be discussing here is a Gilbert model because it's very natural. It lends itself to a bunch of results, which are almost trivial, very simple to compute with a couple of steps, very simple math. I'm not going to insist so much on the math. I'm going to give you some, context and shoot the results. In most cases, it should be easy to understand where they come from. At least that's the effort I'm going to make. So when you say random network, I mean the version by Gilbert, but it's equivalent to the version of Erdős-Rényi. So the version by Gilbert worked like this. You start with n nodes and no links. So all the nodes are present from the beginning in the system. You don't create new nodes. You don't delete existing nodes. They're all there from the beginning. And all you have to do is to decide who is connected to whom. And you do that by checking all the pairs, which are initially, of course, disconnected. And when you focus on a specific pair of nodes I and j, you generate a random number r between 0 and 1, which you can easily do on any compiler/language. If this number r is smaller than a parameter p, which is called link probability, then I and j get connected. You place a link between I and j. If the number r is bigger than p, then I and j remain disconnected. So they are not neighbors. And you do that for all the pairs of nodes. When you do that, when you finish the process, eventually we'll have set some edges and that's your network. How many edges depend on the value of this link probability p. I take the chance to tell you that this routine here is going to be used multiple times when I talk about network models, but also when I talk about network dynamics. When I say that something happens with the probability p, I mean exactly this. Computationally, this is what happens. You generate a random number, you compare it with p, between 0 and 1, and you compare with p. If it's smaller than p, then the certain thing will happen. If it's larger than p instead, it does not happen. In this case, that thing is the existence of an edge between, or link between I and j. Is there something else? What would be the case if r is equal to p? I mean, whatever you want. I mean, you can say that the link is there if r is smaller or equal than p, but consider that we are generally talking about real numbers. So the likelihood that, if you take a random number from 0, 1 is going to be equal to your parameter p is essentially 0, because there is a non-countable number of real numbers between 0 and 1. So you can safely disregard this limit case, but you can also say that you can still set the edge, or you can just leave them untouched. It's not going to make any difference for whatever you calculate on this network, on this model. Thanks for the question. So remember, when I say, and I will say it a few times starting today and even more on Tuesday during the last lecture, when I say something happens with probability p, it could be like a node gets infected when you talk about epidemic spreading, or a node gets an information or gets influenced when we talked about information diffusion, or influence spreading. I mean exactly that. You do that. In the computer, you have to do this. Generate a random number, compare it to the probability, in this case p, and then check if it's smaller or bigger than that value. And then behave, do one thing or do that thing or not do it, or you don't do it otherwise. And in the case specific of random networks, there is a close analogy between the process of edge formation and tossing of a biased coin. You have a coin, just heads and tails. These are the two events. In our case, the two events are I put a link, I put no link. And you have a probability p that the coin shows heads when you toss it. Of course, if p is equal to 1/2, then you have a fair coin. You get with the same probability heads or tails, which is normal for the coins that you're probably mostly familiar with. Now, if you toss the coin t times, This is called, and these are called the independent trials, because every time, the process is independent from the previous tosses. Nothing that happens before is going to affect the outcome of the next toss. And the same thing for the future tosses. The number of heads after t trials, I call the number of heads after t trials equal to h. So h is going to be the number after t trial. I try to use this analogy because hopefully it's going to make clear why we're going to get the formulas that you're going to see about the average degree, about the density, and about also the distribution of degree of the network generated by the random network model by Gilbert. So special cases, if p is equal to 0, it means the coin never yields heads, never shows heads. So h is equal to 0. If p is equal to 1, the coin always shows heads. So the number of heads is going to be exactly equal to the number of trials. If p is equal to 1/2 is the case of the fair coins, and then you approximately, but not exactly, you get approximately half of the, you get heads approximately half of the time, so for half of the trials. And the other half of the time, instead, you're going to get tails. So the general rule is actually that the number of successful trials, so the number of heads, is going to be simply the product of p times t. So this is what you learn from coin tossing. This is what you get when you have a sequence of events which have only two possible outcomes with the same probability, p, independent of each other. But this is what happens in the case of the random graph here, the random network here. So if you want to compute what is the expected number of links, and I call it average, expected because basically you're supposed to average over all the possible configurations of the of the network generated by the model, not a specific instance, in which you can still have small deviations around these averages. So if you take the average basically over the whole copies of the ensemble generated by the model, you can make the same kind of reasoning. So how many links am I going to get if I have n nodes and a probability p of having a link between two nodes? It's the same thing as computing the number of heads with probability of having heads equal to p, and the number of trials is the number of pairs of nodes that you have in your system. So each pair is one trial. It's because I generate a random number, I thought I compare it with p, and then I set my link or I don't set any link. So it's the same thing as a biased coin tossing problem. So now the number of trials is the number of pairs, n times n minus 1 divided by 2. I reminded at the beginning, all of them are disconnected, so there are of course no edges. And the number of successful trials then, like before, is p times the number of trials, which is this. So this is how many links you can expect to find on a random network with n nodes and link probability equal to p. If you check one by one, if you create a bunch of networks like this with the same number of nodes and the same value of probability p, you're going to find small differences around this value, but the values are going to be pretty close to this average. Now, if you want to know what is the density of links, that I remind you we indicate with the letter D, of a random network with n nodes, what you have to do, you have to divide the number of links which are there, which is in this case the expected number of links, D, with, excuse me a second, sorry, I have to take this call, I'll be right back.
Yep, and I can entertain while Santa's gone. Yes, the question in the chat is it the binomial distribution? Yes, so in the discrete sense, it is a binomial distribution. The Erdo-Shreni random graphs in the discrete form, the degree distribution is binomial. In the continuous sense, it turns into a Poisson. But your instincts are right. Yep. Because those are really independent trials. So for each edge, each pair of nodes, you throw a coin, toss a coin. Anywho, Santa's back.
Yeah. Sorry about this. I understand the strategy. Yes. So what did you tell them when because I wasn't in the same room.
I just made things up.
Okay. There's a couple of things here. Oh, is that a binomial distribution, the coin toss? Exactly. You're going to see it in the next slide. Good call. So apparently people are more familiar with this stuff than probably I am. So perhaps I should be there listening to them instead. So it's just a joke. So the density is just basically the ratio between how many links you have there, how many links you can possibly have, which is the total number of pairs, again, n divided n minus 1, n times n minus 1 divided by 2. If I put average, instead of average L, I put this expression given by this, you see that basically the denominator simplifies to the numerator, and what remains is the probability P. So interestingly enough, in this type of networks, the density of links coincides with the probability P. Now, we know, and we've seen it in the table that you see many times, every time we're changing the column that I want to attract your attention, draw your attention to, that real networks are sparse generally. So this number D is very small. So if you want to use this model to create networks that are as sparse as the real ones that you observe, you have to choose a very small value of this probability. Now I want to know, excuse me a second, be right back. To close the door. So I'm in my parents' house, so sometimes, there's more background noise than I wish. Okay, now we should be good. So, so that's the first question. Average number of links, and I told you what the expression is very simple. Density. And now let's look at the average degree. So how many neighbors does a node have on average in this type of network when you build networks with this model? So any node can have at most n minus 1 neighbors, right? Because there are n nodes in total. You have this focal node. So the number of trials in this case is n minus 1. And you have the same probability of having an edge with each of them independently of each other. So just like before, it's the same exercise. The number of trials is n minus 1, which is why I used that comparison, that parallel. So the average number of neighbors is exactly the probability times the number of trials, n minus 1. And here is, sorry, it's binomial. I said the following slide, it was 2 slides after that, because of course, one of the things we want to verify is whether the degree distribution of networks generated by this model is broad, is heterogeneous or not. So, but what is the probability distribution of degree, of the number of neighbors of each node here in this network? Again, we have, what is the probability that the node has k neighbors? It's a coin tossing problem, right? Because like I said, we have n minus 1 trials, and I want to find out what is the probability that I get k heads out of n minus 1 independent trials if each trial is successful with a probability p. This, like somebody pointed out before, so I don't remember the name, apologize for that, is exactly the binomial distribution, which is given by this. I don't want to intimidate anybody. We're not going to see a lot of stuff like this. Most of the stuff here is computational. But this is a fairly popular distribution, and basically says that, you need to have k successes. So each success is a probability p. So you multiply this probability k times because each trial is independent of the other. So you can multiply probabilities. And you also need that the other n minus 1 minus k attempts are unsuccessful. That's why you have 1 minus p, which is a probability that they are unsuccessful, times the number of those trials. On the other hand, since you can have different sequences of this trial, different sequences of heads and tails, you have to account for the entropy somehow, the number of these sequences. So how k heads can be distributed in a sequence of n minus 1 trials. And this is accounted for by this binomial coefficient here. So this is just for those who are more mathematically inclined. I'm not familiar with this, but anyway, we're not going to use this very often. The key thing in our case is that if p is small, as it is, because our graphs are sparse, and I indicated before, and n is large, whatever large means, ideally, of course, we're talking in the limit, mathematically, we're talking in the limit of infinite sides. So when n goes to infinity, but obviously we're talking about real systems here. You don't need to get that far to get this type of approximation. The binomial distribution becomes a Poissonian distribution. It's approximated well by this formula, where average k is the average degree of the network, which, as I told you before, is p times n minus 1. And this is a factorial. And this k, of course, is the number of neighbors of a node. What does a Poissonian look like? It looks like this. Here, this orange curve. It has a peak, and then it goes down very quickly with the value of the variable. So in this exercise, we wanted to see if this distribution could be similar to distributions that we encounter in the real world. So we did this exercise. We considered one of the networks of our collection, but we could take, of course, any other one, which is the OpenFly's world, which is an air transportation network, but not just limited, confined to the US, like the ones I showed you a picture of, but worldwide. So there are airports from all over the place. And I created a network using the random network model, which has the same number of nodes, which in this case are airports, and approximately the same number of links. So I tuned P such that at the end, the average number of links of the model is approximately the number of connections between the airports of this network. And that's what gives me the orange line. So the two systems are comparable in that they have the exact same number of nodes and a very close number of links. But as you see, the distributions are very different. Here you see the comparison one-on-one. Here you see them separately. You can see that the main, here actually is in log-log scale. You see that the blue line stretches up to 200 plus, whereas the orange line does not go past 25. So clearly the range between the minimum and the maximum value of the variable for the blue line is way bigger than the one of the orange line. So and that's actually the lesson, hopefully one of the things we remember. The random network model by Gilbert, but the one by Erdős and Renyi is equivalent, does not generate heterogeneous distributions of degree. It generates unimodal distribution like this one with a clear peak, and most of the nodes will have approximately the same degree. That is, the more true, the larger the network is. And
sorry, can I ask a question, Professor?
Yes.
Okay. Looking at this graph, how different is it from an exponential distribution? That's one.
Which one? Which one?
The orange.
Yeah. Oh, well, for one thing, exponential distribution do not have peaks, right?
Yeah, on the log-log plot.
Oh, on the log, but it's the same distribution. Yeah, of course. You can see somehow the decay, because here we're doing something which is called logarithmic binning that I didn't introduce. It just goes down much faster than exponential distribution. So exponential distribution.
Is there a particular way to show that this is converging to the Poisson distribution, or is converging to the exponential distribution? Is there a way of showing the distribution it's converging to on a log-log scale?
I mean, the distribution converges regardless of the scale, right? So, I mean, the scale can only help you to do plotting exercises or somehow to recognize distributions. The Poissonian distribution goes down much faster than exponential distribution, which is why basically it doesn't stretch as far as the exponential distribution, which also, of course, goes down fast because it goes down like an exponential, and therefore it doesn't reach very far. Here, the whole idea is that here, basically, you get an order of magnitude more, which distribution does not even get close to, compared to a real-world network with the same number of nodes and edges. So that's the whole message here. Then, of course, we can talk about the math. I can show you that why Poissonia goes down faster than exponential, but this is beyond the scope of this course. We can talk somehow separately. You can ask our assistant, but yeah. So this is here. The main thing is that this is unimodal. You see the minimum here is around 3. The maximum is less than 25. Whereas here you go from 1 to 200. So that's the main thing. So the other one is much broader. So there are hubs here and there are no hubs here. And also the peak shows that most of the degrees are between, say, 10 and 15. And like I said, this curve will narrow down and will become even sharper if for the same P you would have a much larger number of nodes. So yeah, so that's the meaning of this. Hopefully it was useful. Like I said, otherwise, please follow up, so with our assistant if you wanted to have more in detail explanation. So basically, we showed that the distribution is unimodal, is homogeneous. There are no hubs. So the nodes are approximately the same degree. That's the main thing. So this, of course, is a problem because this is not what we observe in real networks. The second thing we want to check is the small world property. And there is a very simple argument, which is actually imperfect, but it gives surprisingly well the right result at a high level, which works like this. It revolves around this question: how many nodes are there on average these steps away from any node? since the nodes have approximately the same degree, let us assume, and this is the first approximation, that they all have exactly the same degree k. It's of course a gross approximation, but like I said, if the system is very large, for the same probability p, you're going to get quite a narrow distribution. At distance d equal to 1, of course, there are k nodes because the node has k neighbors. If you go 2 steps away from the focal node, then each of the k neighbors will have k minus 1 other neighbors, different from the focal node. They may, of course, some of these neighbors may be the same. So this is the second approximation we're making. We're assuming here that each of those neighbors will have k minus 1 neighbors which are different from the neighbors of the other nodes. This is another gross approximation, but like I said, this argument instead turns out to be precise in terms of this conclusion. This is just a heuristic argument. And I can repeat the same procedure for larger distances, 3 steps away, 4 steps away. If you keep doing that, so every time you go 1 step away, you reach somehow a shell of nodes, and each of them will have the neighbor that you used to reach it in the first place, plus other k minus 1 neighbors. So if you do this a number of times, you find out that within the distance d from a focal neighbor, for focal node, there are k times k minus 1 to the power d minus 1 nodes. Every time you add 1 shell, you go 1 step away, you add the power k minus 1. Now, if k is not too small, you can approximate k with k minus 1. 25 and 26 are not very different from each other. And of course, if k is even bigger, then this thing is even more. It's another approximation, but this is very small, much smaller than the 2 other approximations I made. So this power here, then, this product, can be then approximated as k to the power of d. D is the number of steps away from the central node. So what did I find? That the number of nodes that I can reach these steps away from any node of a network generated by the random network model is a power of the number of the degree of the nodes. But how many steps does it take to cover the whole network? At some point, of course, I reach all the nodes of the network, so I cannot go further. So the question is that what value of d max, what distance from the focal node do I have to go through so that at the end, basically, I cover the whole graph? So I don't have any more. I reach basically the boundaries of my graph. So that's, of course, again, approximately the case in which this d max such that k to the power of d max is approximately equal to the number of nodes of the network. Because this is all the nodes that I can discover. I cannot discover more than that. So I take the log on both sides with this relation. D max becomes a factor. And then d max, which is what I wanted to know, how many steps away do I have to go from the focal node to cover the whole network, is proportional to the logarithm of the size. I told you last time that the dependence of distances, average shortest path, but also diameter, on the size of the network is an indication of a small world property. It is an indication that this number is going to be very small. And to give you an idea of how small this number is, let's consider a very surreal example. Let's take something close to the world population, which is now actually close to 8 billion people. But we did this a few years ago, and 7 billion was a better approximation. If you replace n equal to 7 billion here, and k is equal to 150, which is called the Dunbar's number. Robin Dunbar is actually a very big scientist and also actually a friend. He said some years ago that 150 is the number of contacts that humans can realistically handle. I mean, you can have more than 150 contacts, but you may not interact equally effectively with all of them. So if you assume that people in general have 150 contacts, this would be our k, n is 7 billion. If you replace it in this formula, you find out that d max would be 4.52. So even if you have 7 billion people, you can reach pretty much everybody within a few steps, a handful of steps in this model. If the real network, the network of contacts, looks like a network generated by the Gilbert/Erdős-Rényi random graph model. So that's good news. That's the second property we wanted to test. So the random network model generates the small world property almost for free. And in fact, like I said, because of the same, since we can repeat the same argument on any network with some degree of randomness, and of course with proper changes, this property is extremely easy to obtain. So in fact, it's not even a very high bar to clear in the first place. The third property I wanted to verify, and last one, is the existence of triangles, so the transitivity property of these networks. So what is the clustering coefficient, the expected clustering coefficient of a node of this network? I remind you, I showed you this diagram yesterday. The clustering coefficient is for a focal node is the number of pairs of neighbors, in this case, the blue dots, which are connected. This would be the 4 red lines, because every time you have one of these lines, you close a triangle, having the red dot as vertex, and divided by the total number of pairs of neighbors, or the number of pairs of these blue balls. So these are the two terms of this ratio. And the question of what is the clustering coefficient is equivalent to the question of saying, so basically, how many of these pairs are close? So how many, what is the probability that two neighbors of a node are connected? Because the probability that two neighbors of a node are connected is exactly like this. Number of pairs which are connected divided the total number of pairs. If I rephrase the question this way, it's immediate to know what is the expected clustering coefficient of the nodes of an Gilbert/Erdős-Renyi random graph. The two models are equivalent, because the probability that two neighbors of a node are connected is the same as the probability that two nodes are connected, because in this model, any two nodes are connected with the same probability, regardless of what happened before, regardless of who they are attached to. So it doesn't matter if the two nodes that you're considering have a vertex in common, have a neighbor in common, like in this case, the probability of them being connected is exactly the same and is equal to P, the parameter, the link probability of the model, which can be rephrased like this. We already established this relation before. It's basically the average degree divided by N. But we've seen that P, in order to match the very low link density of real networks, has to be a very small number, pretty close to 0, in fact. So basically, the result is that the random network model by Erdős-Renyi or Gilbert, this will be the Gilbert version, generates very few triangles. So this is also not great. So let me summarize the situation before we move on to the next model. Links are placed at random, independently of each other. Distances between pairs of nodes are short, so the small world property is satisfied, but like I said, this is really a fairly trivial thing to obtain. And in fact, all the models we're going to discuss today have the small world property. And instead, I mean, the average clustering coefficient is much lower than a real networks of the same size and average degree, which is a bad thing, because we don't want that. We want to have more triangles than that. And the nodes have approximately the same degree. There are no hubs. There are no nodes which have many more neighbors than most of the others. So we passed one check, we failed the other two. The conclusion is that the random network is not a good model of many real-world networks. It's also fair to say that when Erdős and Renyi proposed this model, they didn't know that real networks are heterogeneous, and they didn't know that there were so many triangles, because there were no data about real networks. So, but on the other hand, this is a beautiful model. This is extensively studied. We know pretty much everything there is to know about this network, and it's still very widely used today as a baseline. Speaking about baseline, let me make a small detour. This is not the generative model in the sense that this is a model that explains features that you see. The configuration model, which historically came after, quite a few years after the Erdős-Renyi/Gilbert random graph, is a recipe to randomize, to make networks that you're studying random in order to compare the properties of the networks that you're studying with the properties of the random network. So let me tell you what the question here is. The question is it possible to build networks with a predefinite degree distribution? So I say I have a degree distribution, and I say I have a number of nodes, and I say, can I then generate somewhat a network which has those nodes, and in which then, when I plot the degree distribution is the same of some input curve that I like. The configuration model somehow does almost exactly that. I say almost exactly because it has a more specific focus, a stricter constraint. It builds networks with a predefinite degree sequence. So all the networks generated by the model, in all networks generated by the model, each node will have a predefinite degree. Like in this case, you have these 4 nodes. The green node will always have 3 neighbors in any configuration. The yellow nodes will have 2, the blue nodes will have 2, and the deep blue nodes will have 1. I just give you a simple caveat. You can have one degree distribution, but there may be many degree sequences that lead to that distribution or that can be extracted from the same distribution. In this case, then you can still, in principle, assign slightly different values of degrees to the nodes. But here, let's assume that the focus, because that's the focus of the model, is to preserve the degree sequence, to preserve the degree of each node in any network that you can build this way. So how do you do that? And then I'm going to tell you why you do that, why we still use this extensively. I'm still using it today for at least a couple of projects. The way it works is that you decide what is the degree sequence. You decide how many neighbors you want the first node to have, the second, and all of the others. Once you do that, you attach to each node a number of lines, broken lines like these ones, as many as the degree, the number of neighbors that you want this node to have. So I want the green node to have 3 neighbors. I attach 3 stubs here. They're called stubs. The same thing for these blue nodes, 1 line, 1 stub, 2 for the yellow one, orange, and 2 for the light blue one. And then I close my eyes, I take pairs of these stubs, and I join them randomly. And these are 3 possible configurations you can obtain this way. You can check in each of these configurations, each node will have the predefinite number of neighbors. The green node will always have 3 neighbors. Of course, what happens is that if the network is not so large, and also it depends also how heterogeneous your degree distribution is, that you can also have multiple edges, like here, in this case, 2 edges connecting the same 2 nodes, but also a loop, because you can take, the 2 stubs that you can take can be attached to the same node. If you select 2 of these 3 stubs here and you join them, you get a loop, self-loop. We are considering simple graphs here, and even though if you want to apply the strict recipes, you have to accept these configurations as well, this effect is essentially negligible if the network is sufficiently large. It doesn't happen very often to have self-loops and multiple edges between 2 nodes in most cases. So you can safely neglect it. Even if these configurations, you can just disregard them if they bother you and compute the averages over the simple graph configuration that you obtain from the model. So this is how it works. You attach these stubs, as many stubs as the degree that you want each node to have, and then you combine pairs of stubs selected totally at random. Now, by doing that, actually, you can also generate randomization of the networks that you're interested in. Suppose that you're studying a network, and of course, in your network, each node will have a fixed degree, right? Some number of neighbors. Some nodes will have 1 neighbor, some nodes will have 10, 100, whatever. So you can use this as input to the configuration model and generate randomization. So basically kind of introduce noise into the system so that you basically can replace the edges randomly such that each node preserves the number of neighbors as in the input network. But why would I do that? Why would I care that? Why would I have to randomize, scramble things this way? This is called degree preserving randomization because you preserve the degree of each node. The reason why I do that, why people do that even today, this model is kind of old in the meantime, is that you want to know if some properties, some measures that you make on the original network, if they are depending mostly on degree or on other features of the network. If they depend mostly on degree, you should measure, you should find the same features also on the randomized network. If they don't depend only on degree, then instead, you're going to find that there are some discrepancies in measuring something, which could be clustering coefficient, could be other features or other, for instance, centrality measures that I didn't introduce so far. So it's used as a baseline. So basically, the whole idea is that let's see if my network is indeed a random network which has those degree. So basically, I explain the structure just basically from the degree, and everything else is random. This is kind of a detour because it does not address our main problem. You're not really generating a network here because I'm putting the degrees by hand at the beginning of the game. But historically, it came after the Erdős-Rend model, and like I said, it's extremely popular even today to make comparison, to make assessments about how random the networks that you're playing with are and how much their structural features depend on the degree sequence. Now, let's instead continue with our flow and actually going to more recent times when people instead proposed network models that could explain instead the structure of the networks that we see. Everything starts from 2 basic considerations, 2 features that have been ignored in many cases because there was not much information about real networks, not much data, and no computers to process them. And one of these features, unknown features until recently, was the fact that real networks grow. Real networks, real-world networks are dynamic. I stress that because the random network model by Erdős-Rényi or Gilbert does not grow. The nodes are always there. I start with n nodes, which are disconnected from each other, and then I create the links between them in the way that I showed. But if you think about real networks, like for instance, the World Wide Web started in 1991 with a single node, the first web page ever written. And today there are trillions of them, and it keeps growing every year. And it grows, of course, not in a uniform fashion because some nodes / pages are erased and many others are created. So overall, you have a net balance, which makes this thing grow very fast, even nowadays. Same thing for the citation networks of scientific articles. Every day there are thousands of new articles produced which cite existing papers. So this is a growing network in which there are, of course, every day more papers than the day before and more links between them. The collaboration network of actors, same thing. So here there are, if two actors are starring the same movie, they are connected to each other. And of course, this network grows with the number of new actors joining the system and the number of new movies generating links between pairs of actors starring in them. And the same thing also works in the biological context. If you take the protein interaction network that I described on Monday, this network has been growing over the course of 4 billion years, from a few genes to over the 20,000 genes that we know today. So, but how does grow work, if I want to make a model in a computer? So the way it works is that I have already some pre-existing structure, which is basically what the network is today, and then I introduce new nodes. Like in this case, there is a new node I that joins the system. So then the network at the end will have an additional node. But this node has to decide which of the existing nodes it will become its neighbors. So what makes a distinction in this class of models between a model and the next is the recipe, the criterion according to which I chooses this neighbor. In this case, this node is going to have 3 new neighbors identified by this, represented by these 3 stubs. And in this case, of course, I touch into G, A, and D. I mean, this is a schematic thing. We're going to see how it is done for real. That was the first thing. Networks grow more often than not. There are some recent works about networks shrinking because sometimes there are also systems decaying. So people wanted to also investigate the opposite process. What happens? How does a network shrink? But in most cases, most of the networks that we know are usually grow, and that's why models of network growth have become dominant in this field already since the end of the 90s. The other consideration is that nodes prefer to link to the more connected nodes. This is probably not very surprising if you think about, for instance, how society works. We are attracted by people who are successful, or popular, rich, and the richer they are, the more attractive they become. So, but it's not the only context in which this consideration applies. For instance, our knowledge of the web is biased towards popular pages. We are much more likely to know about popular websites of, say, newspapers or popular figures in sports, politics, history, or science than we are towards fairly unknown websites. And the same thing, scientists are more familiar with highly cited papers. Also, the fact that they are cited, which means that there are a lot of papers listing these papers in their references, in their bibliography at the end of the work, make them also more easy to discover. So not only signal that they are important because obviously they have inspired, they've been a source for a large number of other papers, but it also increases our probability that we discover them, like them, and eventually cite them in our own papers. And then the more movies an actor makes, the more popular they get, and the higher the chances of being cast in a new movie. So this is all very reasonable. So what we need, actually, ideally, is a model that combines these 2 features. A growing model, dynamic model, in which every time you add new nodes, and a model which respects the so-called preferential attachment criterion. New nodes tend to be connected to the more connected nodes, to nodes which have more neighbors. The more neighbors you have, the more attractive you're going to become. The more likely it is that that node is going to get new neighbors. This is not what happened, of course, for the random network model, which was the static model in which basically at the end, all the nodes were equivalent. There was no special attractivity. So this is the recipe of the Barabasi-Albert model, which is of course a huge historic importance because it accelerated the development of network science at the beginning. This is a paper in 1999 published on Science, in Science. So this is how it works, and it was basically a prescription that people then adopted for variants of this model or similar growth models. You start with a group, you need to start from somewhere, and usually start from a small group of nodes, say M0 nodes, which is usually fully connected, doesn't have to be, so in which any two nodes are connected with each other just because it's simpler to start that way. But in principle, as long as you have a few nodes and a bunch of links between them, this is fine. And at each step, there is a new node coming into the system, and this node sets M links with some of the older nodes. The number M being the number of links so the number of neighbors that this node is going to have. And it is a constant, at least in the first version of the model, which is the one that I'm explaining to you. The probability that the new node I chooses an older node J as neighbor is proportional to the degree Kj of J. This is called preferential. This is a preferential attachment recipe. So this expression here means the probability that I chooses J as a neighbor is proportional to how many neighbors J already has, which is Kj, the degree of J. The denominator is used to normalize this, to turn it into a probability, so that when you sum over all the nodes which are already there, all the J, which are potential choices of neighbors for I, that the result is equal to 1. And in fact, if you sum over all J's, you get the numerator equal to the denominator. And the result is going to be 1, as it should be, for this to be a probability. I tell you again, I remind you what that means to do something with a certain probability. It means you choose a random number, you generate a random number between 0 and 1, you compare it to the probability. If that random number is smaller than that probability, then you do the certain thing. In this case, you create the node between I and J, otherwise I and J remain disconnected. And you repeat this thing, adding new nodes every time, one at a time, until you grow the system to the size that you want to reach. If you want to have 1,000 nodes at the end, 10,000 nodes, you do it until you get 10,000, 1,000, 10,000 nodes at the end. So this is the basic procedure to create a Barabasi-Albert or BA model, a network. I want to emphasize that, the fact that the nodes are not picked at random in this case. For instance, if T is a new node and that's to pick the side, let's see. Preferential makes the initial degree distribution broader as the network grows, exactly, and I'm going to show it to you in a second. That's exactly the ingredient that explains the presence of hubs. It's called rich gets richer mechanism. You have a lot and will have even more, and you grow your portfolio faster than the other ones. Specifically, in this case, if the new node is T and he has to choose whether becoming neighbor of I or J, I will have twice the probability of J to be selected because it has twice the number of neighbors of J, 6 versus 3. If you were in the Erdős-Serényi model or Gilbert model instead, T could choose I and J with the same probability. But we don't have hubs in that case. Whereas in this case, because of this rich gets richer phenomenon, the more connected nodes have a higher chance to acquire new links, which gives them a bigger advantage over the other nodes. This is exactly what generates the hubs. This is a picture of a network generated by this model, and the size of the circles is proportional to how many neighbors they have. So you can see here that there are very small circles and there are a few very large circles. This would be the hubs. The distribution of degree, yes, I see that there is a question. Let me finish this thought. The distribution of the degree distribution of the Barabasi-Albert model is a power law, so it's very broad with exponent 3. Is the probability not affected by M? No, the results are independent of M and M0. And again, it depends on how close you are, how mathematically oriented you are. I can give you tons of materials that explain this thing. I can give you it's actually even slides that I used myself in the past in more technical courses, in which I can just demonstrate why the Barabasi-Albert model has that specific degree distribution. It's actually a very nice derivation, which has been used also to derive degree distributions in similar models, mostly variant of the BA model. So the answer is, it doesn't depend on M on M0. It only depends, it doesn't depend on anything. That's actually the reason why the exponent is fixed. Is equal to 3. And that's one of the limitations of the model, because not all degree distributions are power law with exponent 3. And this was one of the motivations to refine the model in the end. I think that there was maybe another thing. Yeah. Is it probably, oh, that would be great, thanks. Yes, reach out about this. I will be happy to share this additional thing. I would like to talk about this, but clearly this was not, could not be the case in the scope of this course. Yeah, yes. Use what are called master equations and so on. So I hope I convince you why this model generates hubs. And this is one of the things we wanted to have. We want to have models that generates networks with hubs, because we've seen these networks everywhere. At the same time, we know that this model, I mean, even though we didn't specifically talk about it, but I showed you how easy it is, this model also has the small world property. In fact, it's an ultra small world, which means that the distances are smaller. The average distance, the average shortest path between any two nodes of networks constructed by the BA model is even smaller than the corresponding number computed for a network with the same number of nodes and links generated by the random network model by Gilbert/Erdős-Trényi. So these are two things. The small world property is there. Like I say, it's trivial. It's not really worth talking too much about this. I showed you how easy it is, why you have this snowball effect with these shells growing exponentially as you move away from a focal node. The same thing happens here with proper refinements. And that we have a heterogeneous distribution of degree. In fact, we have a power law distribution with exponent 3. So these two things are good. What about the third property? Does this model generate a lot of triangles? The answer is not really. So it fails the third test. Why? Because in order to close a triangle, you need to set a link between two neighboring nodes, right? So I'm a new node, and I have to target two nodes which are already connected to each other. But as you've seen in the recipe that determines when you decide, when you set a link or when you don't do it, this only involves pairs of nodes independently of their neighbors or their structure. The only criterion is the degree of the node. So the probability that I get a link to A and B is the same whether they are connected or not. So there is no incentive. There is no mechanism inside this model that incentivizes the formation of triangles. So sadly, despite this big popularity, but they actually solved the main problem, the existence. It explains how the hubs can be generated by the rich gets richer or preferential attachment mechanism. This model does not explain why real networks have such high values of the clustering coefficient, why there are so many triangles. So we need some mechanism that incentivizes, that closes this triangle. And that's the last thing I'm going to talk to you about in terms of model. I'm going to close the circle. I'm going to introduce a simple model, which did not have the success it should have had. It's not a model of mine, so I'm very candid in my assessment. I don't get any advantage by advertising this model, any personal advantage, but I think it closes our circle because it's a very simple model that it checks all the three boxes we try to check from the very beginning. Basically, it ends the quest for a model that does the key things that we want to have. So this is how it works. So you may see that, I mean, some of it looks similar to the preferential attachment recipe. You start from a group of, it's like, this is a growth model again. So it's a dynamic model in which you add iteratively new nodes, and these nodes will have to form links with the existing nodes. So you start from a group of M0 nodes, which is usually fully connected. They click exactly like the preferential attachment BA model. At each step, a new node I is added to the system and sets M links with some of the other nodes, just like in the other model, and in pretty much all these models, dynamic models. But then, I mean, this is what makes it different. The first link, the first neighbor is chosen entirely at random. Starting from the second, third, if you set more than one link, you see here the number of neighbors that the node establishes is bigger than 1. So you need to have at least two new neighbors per node. And you're gonna see why, because what you do with the first link is different from what you do for the following link. So you need at least two links in order to somehow complete the recipe. So the first link is set at random. You just choose a target at random. Close your eyes and pick one of the existing nodes, regardless of their degree, which is great. It's very simple, very intuitive way. Basically, you bump into somebody. But starting from the second link onwards, you can either form a link with a neighbor or the first neighbor you chose, J, with probability P. Any neighbor J, you can choose at a random, or you set a link with another randomly chosen node. It may look a bit overwhelming, so let me show you this diagram that hopefully will clarify things. So this is my network, this is where I was. And there is a new node coming here. The first thing that it does, it chooses one of these nodes at random. See, it's a random target, J, and it forms a link there. This would be the red line here. The successive neighbors of I are chosen this way. With the probability P, is going to be a neighbor of J randomly selected. In this case, this green node. You see, the moment I hit this node, I close a triangle, which is what I want to do. So the larger the probability of doing this, the larger the density of triangles in my system, which then can be tuned by choosing properly the value of this probability of triadic closure. It's called triadic closure because the triangle is also called a triad. And otherwise, with the complementary probability, so, and I told you what that means, you generate a random number and so on. Hopefully you know that, and I told you that I would repeat this multiple times. So hopefully the message went through. Otherwise, instead, you pick another node at random. So this is how this model works. It's even simpler in some way than preferential attachment. You don't have to compute probabilities. The only probability is P, and therefore 1 minus P. Otherwise, you choose things at random. Now, if you study this model, and it's been done already 20 years ago when it was introduced, 20 plus years ago, you find that the degree distribution is heavy-tailed. So this model generates indeed hubs. The average clustering coefficient is, of course, much higher than in BA networks because there is a mechanism that generates triangles, the one that you saw, this triadic closure with probability P. The more triangles, the larger the probability P, the more triangles you have in the system. And actually, an additional thing is that somebody asked this yesterday. When the triadic closure probability P is sufficiently high, that you have a lot of triangles, when P is close to 1, the network also forms modules, communities, which is this part of network science that I spent most of my professional life on, and I decided to not to cover in this in the context of this very short course. How can we explain this model generating hubs despite no explicit mechanism supporting it? Great question. This is the topic of my next slide. If links are set at random, as it seems, how can the model generate hubs? So, really we're following the right way, or maybe I'm just lucky here. This is the answer. Consider what happens when you close the triangle. You choose a node, and then you follow an edge attached to that node, and that's your target. The link is the edge or link is chosen at random because you can form it. You can choose any neighbor of the target node. I told you, I think yesterday, that if you pick, and that was the result and the reason, the rationale of the friendship paradox, if you select or sample nodes following links, you have a higher chance of bumping into hubs. Because clearly, the more links, the more neighbor I have, the more links are attached to me. And if somebody chooses a link, the higher the probability that this link is attached to me. So basically, this very simple, very intuitive, and that's why I love this model, despite the fact it's not my model. I wish I had done it, but I didn't even know about networks at the time. The beauty of this thing is that the mechanism of triadic closure induces effectively preferential attachment on the nodes that you target at the end. But you do it in a very natural fashion because you don't really know what is the degree of the node. You don't compute these probabilities. You don't have a feeling. So, so this is where the hubs come from, because the moment you connect with a neighbor of this target node that you picked at the beginning, the probability of picking that neighbor is proportional to the degree. But this is a preferential attachment in disguise, or effective preferential attachment. The take-home message which comes with this model is that preferential attachment can be induced by simple mechanisms based on random choices. I choose a node and I decide to be a friend to the neighbor. If I do that, I effectively do a preferential attachment. And that makes the whole thing more believable because, we like random choices. It's easy to convince people that things happen at random, because otherwise you have to make assumptions which can be easily criticized. So thanks a lot for the question, but I was going to cover this next. So thanks a lot. Okay, actually it starts to be, okay. Monica, I hope that this was clear. So, because you're not choosing nodes at random anymore. The moment you choose the neighbor of a node, you're basically following links. And if you follow links, you have a high probability of bumping into a hub. So you're effectively doing preferential attachment. Would the clique not have a homogeneous distribution? How would BA preferential attachment work with the clique as starting point? That's a good point. So why would I get the hubs if at the beginning all the nodes, if they are part of a clique, have the same number of neighbors? Because of stochasticity. So what happens at the beginning is that the nodes that are chosen first in a totally stochastic and random fashion we start to have a little bit higher degree, and that gives them a slightly higher probability of being selected in next round. And if you do this over many iterations, eventually they will stand out and they will create a big gap with the other ones. So that's a great question too. Does the degree distribution follow power law? It does. That's the clustering coefficient. Sorry, for the random walk model, not exactly, but it's close. Actually, we wrote a paper about this. So if you want, it follows what is called a Weibull distribution. And there is a proof of this. So I can point you to the paper if you want. Please remind me of this. And does a clustering coefficient mimic real-world network? It can get pretty close to the values that you see, some of the values that you see in the table. So depending on how big P is. If P is close to 1, then you can really create a lot of triangles. Because basically then you have always triadic closure. So you close a lot of triangles because almost every time you try to close triangles. So of course it's kind of enforced. You're doing it almost by hand, but at least you can still tune it by choosing the value of P. Okay, great job. And we still have a few minutes, so that allows me to start our discussion about dynamics. I was really keen on starting this discussion today because tomorrow we'll have to start thinking about your project pitch. And like I said, you can obviously go through the slides of the last class, which are already available, and we see which other dynamics we're going to discuss. But I wanted to make you aware because this is usually dynamics is, very often is the most exciting part of networks, assignment, things and so on. I'm also a methodology. I work most of my life on structure, but I understand why these things can be captivating. They ring bells with people. And hopefully I'm going to do the same with you. So let's talk about this. This is actually the final module of the course. So we started today because this way I can cover more processes by the end of the course on Tuesday, of the classes on Tuesday. So what do we want to do here? We have our network, whatever it is, a network of contact, network of friendship, Twitter network of retweets, or an information network, anything. And we want to run some processes on this networks. If it's a network of contact, for instance, the process could be the spreading of an infectious disease. And we're going to get to that on Tuesday. Like I said, the info is already available. So the principle is that you define some states of the nodes, which in our case are mostly like on and off, like for instance, infected, not infected, informed, not informed, or one opinion or the other opinion, and so on. But you can also have multiple states. And then you introduce a recipe that tells you how the state of this node, of each node, is affected or affects the state of the neighbors of those nodes. The examples that we cover here belong to 3 broad classes: information diffusion, classes of processes, which are extremely popular and they generated tons of literature, information diffusion, epidemic spreading, and opinion dynamics. So let me start with information diffusion. I don't have to convince you that information diffusion is critical, especially nowadays, and not only information, but also fake news, misinformation. I think you heard a lot about this. And and also, of course, work with people who are experts of this. But the thing is very clear, the networks, interactions between people are critical to the diffusion of information. We may buy a new phone because a friend has bought a new phone. Say, oh, look, it's so great, I bought this now, and so on. You start to pay attention, you make your research, and at the end, you decide to do it. But without perhaps this interaction, without this exposure to this new product, maybe you would not have done it or not so soon. You may also discover a piece of news because friends forward it to us. Oh, look what I read today. Or have you seen, I found this nice Nice photo. Yesterday, a friend of mine sent me a very, very funny picture that I didn't know about through Messenger. This is called social contagion, how individuals' opinions, beliefs, ideas influence or are influenced by their neighbors in social networks. And that's what we're going to be discussing pretty much between the next few minutes and Tuesday. So let me start with information diffusion. I'm going to introduce very, very basic setups, but they're enough somehow to derive a bunch of nice things. And with small variations, you can also design your own model, if that's one of the things you would like to try, as a project. So this is a standard setup of models of influence or information spreading. They work pretty much the same way. You start from a certain number of nodes which are initially activated. These are called influencers. Could be the first people who buy a new phone, a new product, or they adopt an idea or innovation or a certain behavior, like quit smoking, for instance. Each inactive node is activated or not according to some rule that depends on the presence of active neighbors and or other factors and parameters. So you do this activation. At some point, no activation is possible. That's what usually happens in the simplest models. And then you see how many people have been activated by the initial set of influencers. And usually there are, what happens from the initial configuration until you reach convergence and you cannot influence any more people is what is called an influence cascade. It's a cascade succession of activations of nodes which were not initially activated, and these cascades can be of various sizes. The most interesting case, of course, and in many ways could be the most favorable or the most dangerous if you're talking about information and misinformation spreading, propaganda or fake news, is that a small set of people or agents / nodes here could manage to affect a sizable proportion of the whole system. This would be what we call a global cascade. In this very simple example here, the focal node would be the one in the middle. It has 4 neighbors, 2 are active, indicated by the red dots here, and eventually becomes active because of these 2. But it is, of course, high level. I'm not saying the rules or anything. We're going to give some specific example. Specifically, I'm going to introduce you one of the 2 main classes of models used to model, to characterize and follow information diffusion, influence diffusion, which are threshold models. Models have been around for a long time, and they are based on the idea of peer pressure. I change my behavior. In this case, I get activated. I become active if enough people around me are active. If I have enough, if the effect of the people around me, the effect of my contact exceeds a certain level. The level being called the threshold. So let me tell you, give you the most general recipe, and then we're going to specialize. We're going to make it simpler and simpler for hopefully a better understanding. In the linear threshold model, you compute so the influence acting on a non-active node from their active neighbors is just the sum of the weight of the links connecting the node I to all the active neighbors j. So I am node I have a bunch of neighbors. Some of them are active, some of them are not. I forget the ones which are not active. I consider only the ones who are active. And I consider the links, the links connecting me to those active neighbors. They will have certain weights in the more general situation in which the network is weighted. And I sum those weights. I sum the weights of the links connecting I to its active neighbors. That's what's exemplified by this formula. And Wji is the weight of the link going from j to I. Because it can also be directed. And in this case, Wji and Wij may not be the same number. The activation condition is that if this expression that you see here, the influence on node I exceeds a certain value, which, as you see from the subscript, generally depends on the node, because not everybody has the same, is as easy to convince, to be convinced than others, then I becomes active. Now, if for simplicity the network is unweighted, because now we're going to simplify things so that the examples are also easier to grasp, then I don't have weights on the edges. And when I consider only the active nodes, the influence acting on I is simply the number of neighbors which are active. So the number of neighbors of I which are on. That's why I put on here. So in this case, it's this number which has to be larger than a threshold. I need to have enough active neighbors to become active myself, to buy the new phone, to vote for a candidate, or to quit smoking or anything, whatever the outcome of the influence is. If all the nodes have the same threshold, because right now the threshold depends on the node, again, because it's the most general case, then you have this simple expression. We're going to play with this because it's simply, just simpler to understand. So let me give you the model dynamics here, the main bits. Initially, some nodes are activated, for instance, a random number or a random proportion. You can have, I don't know, it depends how big your network is. You can have, I don't know, a single influencer or 10 influencer, or you can say like 1% of influencers. So if your network has 1,000 nodes, 1% is 10. So initially, I'm going to have 10 influencers, which are nodes that you can usually select at random or with a certain criterion. In fact, one of the pitches that I'm going to offer to you tomorrow, without any obligation for you to do anything, is about this issue, this problem of influence maximization, how to choose the set of initial influencers such to maximize the size of the influence cascade. A classic problem in social network dynamics. All the active nodes remain active. So if you're active, you're always active. What can happen is that some inactive nodes may become active, and they can then in turn influence other nodes to become active and so on, triggering a cascade. Each inactive node is activated if the number of active neighbors is at or above its threshold. I just want to quickly say that there are two different ways of updating the node states. I'm saying that because this is a very general choice that you have to make on all processes, simulation processes, even epidemic spreading, opinion dynamics, and so on. You have to choose to do one of these two things. The asynchronous update, which is the one that I've been using for a long time, basically means that every time a new node is activated, then when you activate, when you try to check whether new nodes are activated, you're using the new configuration with a newly active node. So the configuration basically changes a little bit, and every time it changes, of course, you're using the new configuration to make the next decisions about activation. The synchronous update instead works like this. Basically, the situation is frozen as of the end of the previous iteration. And every time you decide whether an active node becomes active or not, you only consider which active neighbors the node had at the end of the previous iteration. And then for each node, you say, okay, this will be activated, this will not be, this will be, this will be. And then once you put these things together, you make all these activations at the same time. That's why it's called synchronous, because basically you're considering the same configuration of the system when you make the updates. But pretty much you're going to get at a very high level the same results. So it's not going to affect the results. It can affect the number of iterations until you get convergence. And so it can affect mostly speed, but it's not going to change the narrative. Now, the last thing I want to tell you is that, so far we consider the actual number of active neighbors, but since not everybody has the same number of contacts, it's hard to believe that, for instance, a person who has hundreds of contacts could be convinced by a single person or a couple of persons. It can happen, of course. It depends on how influential those people are. But probably make more sense also in the context of this peer pressure kind of scenario, that the peer pressure is measured not just by how many people are trying to convince us to do a certain thing or influence us, but what is the fraction, the proportion of people in our neighborhood that tries to do that. So instead of considering the actual number, I divide this number by the degree, the total number of contacts. So I want to know, as long as like 20% of my neighbors or more act on me, then I'm gonna be acting myself. So this would be, of course, will make somehow things a bit more uniform, regardless of whether a person is a hub or not. And that's part of its fascination, because in this case, basically, you're using a threshold, which is a number between 0 and 1, because this ratio cannot be bigger than 1. And you can more easily also use the same value across different nodes. For instance, if theta in this case is equal to 1/2, at least half of your neighbors must be active for you to switch to the active state. And it may be easier if you have only a couple of neighbors. It may be more complicated if you have 200 neighbors. So it really depends. So let's see what happens in this case. I'm going to show you some snapshots quickly. We're almost done. I'm sorry if we're going to go a couple of minutes over. Hopefully you can resist until then. This is my network, very simple as you see, and this is my initial condition. The only node which is the only influence I have at the beginning is node 1. So the threshold is 1/2. This is a fractional threshold model. So in order to switch to the active state, I need to have at least half of my neighbors in the active state. So this is the case for nodes 2 and 3, because 2 has only 2 neighbors, and one of them is 1. So which is exactly half of its neighbors. So 2 switches to the active state, and because of that, also 3 switches to the active state. 4 also has 2 neighbors, 1 and 5. 1 is active, so 4 becomes active. Likewise, you can easily see that if you move to 5, 6, 7, and so on, for instance, 5 now has 3 neighbors, but 1 and 4 are active, which is 2/3 bigger than 1/2, and therefore 5 becomes active, and so on. At the end, basically, the single influencer managed to trigger a cascade that affects everybody in the system. So if the network is sparse, whether or not the cascade is triggered depends on its structure, depends on what the node's degree is in particular. And a good context to generate a global cascade is to have a lot of so-called vulnerable nodes. The vulnerable nodes are the nodes that can be activated by a single active neighbor. So the moment one of their neighbors becomes active, then they become active too. So since the condition for activation now in the fractional threshold model is that the fraction of neighbors which are on has to be bigger than this threshold. If we want that this thing is satisfied when only one of the neighbors is active, I replace ni on with 1 here in this formula, and I get So you can easily see then when you choose a threshold, the thresholds of the nodes, how many vulnerable nodes you have. Those are particularly tricky. I see here your network internet connection is unstable. I hope that you didn't lose any of this. Please let me know otherwise. Satyaki, did you lose my voice for a second?
No, I think you're good.
So there was no moment. Sorry, I just got this message here. Luckily, we're basically at the end.
No, I didn't catch it.
Okay, all right. Hopefully for everybody. So vulnerable nodes, the more you have, of course, the more easily you can trigger a cascade, because these nodes can be easily convinced as soon as one of their neighbors becomes active, then they will switch to the active state themselves. And you can wonder, who are the most effective influencers? This is one of the big questions, also around this issue of influence maximization. Hubs are usually, as you can expect, very effective influencers, right? They have many contacts, and therefore they can exert their influence on a larger number of people. But being a hub does not necessarily imply being a good influencer. You can also manage to do a good job if you are depending on the position of the node. So if you are in the core of the network, you can trigger a cascade more easily than if you are in the periphery. For instance, if I take the same system that you've seen before, and I start, my initial condition is that node 7 is active and no more 1, the cascade stops after I activate node 6, because node 1 has 5 neighbors, but only 2 of them, has 5 neighbors, but only 1 of them is active, which is 7. So it's not going to switch to the active state. And 5 has 3 neighbors, but only 1 of them, which is 6, is active. And that's 1/3, which is smaller than 1/2. All of these things, which seem very intuitive, instead, of course, in the context of more complex models and complex dynamics, are regularly used by companies, for instance, to do what is called cascade control, to see which people you need to convince or which people you have to pay as testimonial to diffuse your message. It's not obvious that even if you pay a lot of money, hiring Taylor Swift alone is going to generate a global cascade. Actually, it seems that it's exactly the opposite. You need to focus on middle-sized influencers, so you can divide your budget among multiple people, and overall you can get a bigger effect than focusing a single big hub by itself. And this are crucial for not only for the key influencers, but also in the so-called field of viral marketing, in which you use social networks to promote different type of products or propaganda or ideas. Okay, that's all I wanted to say today. Sorry if I went a couple of minutes over. There were also a bunch of questions, but I'm happy about it because it shows at least that you're following, and I thank you for that. If there is anything else that you want to ask me on this stage, please do it now or ask our assistant in a couple of hours, I believe. Actually, an hour and a half, right? We're going to have a TA session today. Solve the remaining of the end of the course. Let me see. Thanks a lot, Martin. This is very sweet. I don't agree, but it's nice to have fans. And by the way, some of you asked me for more material. So I don't want to share this with everybody because for most people it may not be as interesting than for those who asked me for this. So please reach out to me directly. You should have my email because until yesterday I sent email to you. I promise I'm not going to send you more than perhaps one or possibly two emails until the end of the course. We're going to use mostly Slack to communicate. I wanted to make sure that I gave information to anybody. Last question, is asynchronous update analogous to explicit time integration? I'm not sure I know what explicit time integration is. Does it then have a stability criterion for the time stepping? I'm sorry, I confess I don't know what explicit time integration is. So perhaps, if you want to send me a more detailed context by email, I'd be happy to address that. So I confess I never heard about explicit time integration. Asynchronous basically means that your system change every time you change the activation state, or usually since active nodes cannot become inactive, every time an inactive node becomes active, then basically you keep the change there. And when you do your next update, you consider the new situation with this new active node. On top, of course, of the other ones. So that is the only thing that I want to go through. And the reason why I spent some time on that, despite this not being critical, is the fact that you have to do this choice for any, not only social simulation, but I would say any agent-based simulation you wanna do in your life, even without networks. Even if you just play on a lattice and so on, you have to decide whether your updates are going to be synchronous or asynchronous. That's why I still spend 1 or 2 minutes to explain this, because you may bump into this even outside of the context of network science. Okay, so if there's nothing else, thanks for your patience, also for staying a bit over. Like I said, if you have questions, use the Slack, ask our TAs, and otherwise see you tomorrow.
Hi, Santo, I have a question.
Oh, please.
So is there a configuration model for predefined clustering coefficient of nodes?
The configuration model, the only thing that it does, it just respects the degree sequence of the original network. So one way you can use this in the context of the clustering coefficient is that you study a network, you measure the clustering coefficient, the average, of course, over all of them, or if you want the distribution of the individual clustering coefficients over all the nodes, which is distribution like the degree distribution. And then you can see, do I have all these triangles because of some hidden mechanism of triadic closure, like the one that I illustrated in the random walk model? Or it's degree, or it's just the fact that I need to have these connections for each node and so on, enough to explain why all these triangles appear. So you use a configuration model, you therefore randomize all the connections, you only preserve the number of neighbors of each node, and then you measure on these configurations what your distribution, the clustering coefficient is, or what the average clustering coefficient is. If you find a big difference, then probably, and it depends in which direction, usually the difference is in the direction of having many less triangles than in the initial system. Then you can see maybe there is a mechanism in the network that I'm studying, that I'm interested in, that generates triangles regardless of degree. And that could be information that you didn't necessarily have at the beginning of your investigation. So you can start say, okay, maybe then I have to look in specific direction. Degree alone is not enough to explain the value or the behavior of this variable. This is why even today the configuration model is used to create baselines, to compare, your network with a network in which everything is just explained by degree, but it is essentially random. So thanks a lot. Yes.
What I mean is that like I use a constraint that I will keep the clustering coefficients of each node is fixed, whether I can generate a model for that.
Oh yeah, of course you can do that. In fact, I may even heard, sorry, Maidan, I didn't get your question the first time. Yeah, actually, I mean, that of course, you may not call it configuration model, you may call it different. You can, I don't know, you can call it a transitivity model. We are very flexible about names. I may even heard about this. Oh, actually, let me tell you one thing. But again, I mean, we could talk for hours about this. We don't want to bore people also, if you want to. But in the past, for instance, one question that looked like a big question, like was more than 10 years ago, even before I moved back to IU, was, so how many constraints do you have to put in your system to reproduce as much as possible the original network? So like I said, I respect the degree sequence, and that's not enough usually. You can measure a lot of stuff which is going to be different in the initial system and in the randomization. But on top of that, I can introduce other constraints. For instance, I can preserve what is called the 2-point degree correlation. So the relation between the degree of a node and the average degree of their neighbors. This would be another constraint. So you respect the degree sequence and that. And then we also introduced something like that. Not exactly the clustering coefficient of each node. That was difficult to respect. It was difficult to close a network based on this constraint. But a curve that says how the clustering coefficient of nodes with the same degree varies as a function of k. And we found out that if you do this, if you randomize the network by respecting the degree sequence, by respecting this 2-point correlation, and by respecting this function, that you get very, very close to the structure of the network. Basically, that those constraints basically explain why the network looks like that. If you want, I can give you a reference to that. But yeah, in principle, of course, you decide what kind of constraints. You are randomize the network by preserving something. The configuration model preserves the degree sequence, but it doesn't necessarily have to be your choice. It's a very natural thing to do, but you can decide to preserve or